In this video, we're going to learn how to solve polynomial inequalities. Now, we'll start by first doing it by looking at a graph, and then I'll show you how to do it algebraically. So, just looking at the graph, we're going to solve this polynomial inequality, x plus 3 minus times x minus 1 squared is greater than 0. The reason why we're going to use a graph is that if it's greater than 0, it means it's above the x-axis. All the y values are greater than 0. So just looking at this graph, I can see that it's greater than 0 between negative 3 and 1. Negative 3 is less than x, which is less than 1. But I don't include 1 because it's 0 at 1. And 0 is not bigger than 0. The other interval I can see that is greater than 0 is whenever x is greater than 1. For all x values bigger than 1, it goes up forever. This section over here is below the x-axis is less than 0, so I do not include it. So for my answer, I'm either going to put the set that x is all real numbers such that x is between negative 3 and 1, or x is greater than 1. Now, if you were using interval notation, you may write this as negative 3 to 1 union 1 to infinity. Those are two ways to represent your answer, and I'll do this for every solution, so you can always see both ways to write your solution. For the next one, we have negative 2 times x plus 2 times x minus 2 cubed. So here I want to know everywhere it's less than or equal to 0, which means below the x-axis, but including 0. So I can see that it's below the x-axis whenever x is less than or equal to negative 2, and whenever x is greater than or equal to, because it is equal to 0 there, 2. So my solution would be all real numbers x, such that x is less than or equal to negative 2, or x is greater than or equal to 2. In interval notation, this will look like negative infinity, comma, negative 2, but with a bracket to include the negative 2, union bracket 2 to include the 2, infinity. So the top is a set notation, the bottom is an interval notation. Both mean the same thing, just look a little bit different. Now let's say you do not have the graph for it. Well, you have to start off by first moving all terms to one side. So in this case, we'll have x to the fourth minus x is greater than 0. So a nice way to look at this problem now is not to figure out like what this graph looks like at this point, but to actually figure out where is it equal to 0, and I can actually break up a number line to see where it's above or below the x-axis. But I need to find out where it's equal to 0 first so I can make that number line. So I'm going to solve the equation x minus 4 minus x to the fourth minus x equals 0. So first I'll factor out an x, since that's a common factor. And I can also factor x cubed minus 1 using difference of cubes, which will be x times x minus 1 times x squared plus x plus 1. This is how you factor a difference of cube situation. And then we can set each factor equal to 0. X equal to 0 gives me 0. X minus 1 equals to 0 gives me x equals 1. And x squared plus x plus 1 equal to 0, its only solutions would not be real. If I use the quadratic formula, I would end up with negative 1 plus or minus the square root of negative 3 over 2. But the square root of a negative 3 makes that an imaginary number, so I do not include that as a possible 0, since graphically you would not see that 0. So I'm going to look at 1 and 0. So I'll make a number line for my x-axis, and I'll mark it up with 0 and 1. So my intervals would be from negative infinity to 0, from 0 to 1, and from 1 to infinity. Then I'll pick a number on each of those intervals. So for example, -1 on the first interval, 1/2 on the second interval because it's between 0 and 1, and 2 on the last interval because it's greater than 1. When I plug -1 into this expression, again, this is for the function x to the fourth minus x. -1 to the fourth is 1 minus -1, which gives me 2. So f of -1 equals 2, which since that's positive, I know it's above the x-axis. When I plug in 1/2, f of 1/2 would be 1/2 to the fourth, which is 1/16, minus 1/2, which would be -7/16, which is negative, so we're below the x-axis. And then 2 plugged in would be 2 to the fourth, which is 16 minus 2, which would be 14, which is above the x-axis. So looking at this function, I'm looking for where is x to the fourth minus x greater than 0. That's when it would be above the x-axis. So my answer would be all x such that x is less than 0 or x is greater than 1. Or if I use those intervals that I wrote earlier, I would write my answer as -infinity to 0 union 1 to infinity, but not including 1 or 0 since it's not, this inequality is not equals to. Let's do another example. So here, move everything to one side first. So we'll have x to the fourth minus 9x squared is less than or equal to 0. So now I'm looking for when is the function x to the fourth minus 9x squared below the x-axis. So I would first just set it equal to 0 to find out where does it touch the x-axis so we can find out if it's above or below. So factoring out x squared, I get x squared times x squared minus 9. Factoring x squared minus 9, I get x plus 3 and x minus 3. So my 3 spots where this function is equal to 0 is that x equals 0, x equals -3, and x equals 3. So I'm going to make a number line and label this 3 points -3, 0, and 3. So my intervals will be -infinity to -3, -3 to 0, 0 to 3, and 3 to infinity. Now I'll pick a number on each interval to plug in to see what the value would be. So I'll plug -4 for this interval, -1 for that interval, 1 for this interval, and 4 for the last one, because these numbers are on that particular interval. Now when I plug in -4 into my expression, -4 to the fourth power is 256 minus 9 times 16. Now those numbers are a little big, so I'll just plug it into a calculator. So -4 to the fourth power minus 9 times -4 squared. Give me a positive 112. I'll plug in -1, which would be 1 minus 9 times 1, because when you raise the number to the fourth or second power, it becomes positive. So 1 minus 9 is -8. Plug in 1, I'll also get -8. Then plug in 4, I'll get the same value that I did earlier. F of 4 would be 112. And the reason why I know that is, again, raising the number to the fourth or second power will always yield a positive number. So whether it's positive or -4, it should give me the same value. So I see here that I am above on that interval, below on this interval, below on that interval, and above on that interval. And I'm looking for whenever I am below or equal to 0. So here I can see that it happens from -3 to 0. But I definitely want to include -3 since I know it's 0 at -3. And I definitely want to include 0 since I know it's 0 at x equals 0. And it's on the interval from 0 to 3, so including 0 and including 3 since it's also 0 at 3. So seeing this, I know it's including 0, so I don't actually need to write two different intervals. I can actually just write the interval from -3 to 3 as my answer. And in set notation, what that would look like is all values of x, all real values of x, such that x is between -3 and 3, but including 3. So you'll see here I'm using equals to on those inequalities instead of not equals to. And that is how you solve polynomial inequalities.